Any homework questions? Yes. On vectors? Okay, so vectors. Number 16. Horizontal vertical coordinate system. So just the coordinate system like we're used to. And the origin is at the center of mass of, so we have a 1/2 meter long cable attached to the body. There's no picture for this. Oh yeah, there is. Oh, okay. Okay, so center mass is here somewhere, so that's where the origin is really, not where I drew the coordinate system. That just shows the orientation of the axes. And you have like a pin joint there, and a cable connected here that connects to the wall. And it says that this cable makes a 45-degree angle. It doesn't look like that right now. Change that. Okay, so 45 degrees. It attaches to the body at 0.6, 0.4. And it has a length of 0.5 meters. And the pin, this point down here, is 0.05 for x, negative 0.2 for y. And we know that the cable has a tension T. And we want to know two things. So first, what's the force vector that the cable applies to the body? And then second, we want to know the vector from the pin to the point where the cable contacts the wall. So from this point, 0.05, negative 0.2, to cable's wall contact. Okay, so that's up this here. Okay. Okay, so first, this is something we're going to use a lot. So we need to come up with, we know that the magnitude of the cable force, the force that the cable applies to the body, is T. Okay, and we know the direction. So we know it's in that direction with a magnitude. And the way we're going to do that, express that vector, is come up with a unit vector in that direction, and then multiply that unit vector by T. And if t was 1,000, we'd multiply by 1,000. We're going to use that idea all the time. Like pretty much any time you have a force applied by the cable, we're going to use that idea. Okay, so we know that the force is equal to the magnitude t times a unit vector, and that unit vector is in this direction. And so to come up with that unit vector, we have that angle of 45 degrees. So think of just putting, so there's the coordinate system. We have an angle of 45 degrees. And so the unit vector is just equal to cosine of 45, sine of 45. So 0.7071, 0.7071. As far as significant figures, for every unit vector, I use 3 significant figures, except 45 degrees, I use 4. There's no reason for that at all. That's just what I do. So I don't care about significant figures. Because, I don't know, you probably all have to take chemistry, and then they'll make you worry about significant figures enough for all of us. Okay, so that means that the force vector is this unit vector times t, so 0.7071 t, 0.7071 t. And the beauty of that is if we just think of this as an unknown vector, so say like, well, we don't know what that force vector is. This is a 2D problem, so how many unknowns does that vector have? 2, the x and y components. But if we realize that we know the direction, it's only the magnitude we don't know, we can represent the direction with that unit vector, multiply it by a single unknown, and now we've gone from 2 unknowns to 1. Okay? And so that idea is really important. It comes up all the time, more in statics than in dynamics, but it'll come up a lot. And then the second question is, well, we want to come up with a vector that goes from the pin to this wall contact, so something like this. Okay. We already have coordinates for this point. Those were given. Okay. So if we come up with coordinates for that point, we can just subtract. These coordinates minus these coordinates. Okay. So for part B, let's just get the coordinates of that wall contact. Well, a vector that goes from the cable's contact with the body to the cable's contact with the wall. Let me just sketch this shape again. Okay, so a vector that goes from here to here. I'll call that U vector, as opposed to up above I called it U hat because it's a unit vector. Let me try to get the color scheme to all agree. Okay, no, this is U vector. Okay, well, that vector has the same direction as the unit vector we did in part A. It just has a different magnitude. That force magnitude was t. The magnitude of this vector, since the cable has a length of 0.5, magnitude is 0.5. So we can think of this vector u as just equal to 5 times cosine of 45, 0.5 times sine of 45. I'm just multiplying by that unit vector. And that is 0.3535, 0.3535. And now all we have to do is, so to come up with the coordinates of this point, we can just add the coordinates of this point to that vector. You can just always think of coordinates are always just vectors from the origin to a point. So the coordinates here, 0.6, 0.4, are just a vector from the origin to here. And then to come up with the coordinates there, we're just adding the vector from origin to 0.6, 0.4 to this new vector, 0.35, 0.35. So the coordinates of the wall contact are 0. What did I say that is? 0.6, 0.4, plus 0.3535, 0.3535, and that's 0.9535, 0.7535. Okay, so this gives the coordinates at the wall contact. So then the vector we can just subtract. So vector to the wall contact from the pin is 0.9535, 0.7535 minus the coordinates of the pin, which were 0.05, negative 0.2, and so you get 0.9035, 0.9535. Any questions about that? And then 19. So the beam has a length of 4 meters and it's angled at 45 degrees. Length is 4 meters. The left end is connected to the ground by a pin, which slides in a slot that makes a 20-degree angle with the vertical. Okay, so there's a pin here, slides in a slot. Like this, and this makes an angle of 20 degrees with the vertical. And then there's a pin up at the top. Connecting it to the wall. So what's a vector with magnitude r that's perpendicular to the slot? So the main thing we have to do, so the force vector, this is for part A. The force vector is going to be equal to the magnitude r times the unit vector. And the main challenge is coming up with a unit vector that's perpendicular to that slot. There are two vectors perpendicular to that slot, because that slot is a line. It doesn't have a up or a down, it's just a line. And so for any line, there's two vectors perpendicular to it. So let me draw this. So there's the slot. And that vector is perpendicular to it, and that vector is perpendicular to it. We can choose either one of those because it doesn't specify. So I'm going to choose this one. Why not? And when I'm doing, this is getting to the point where, so most of the time in problems, you can just sort of eyeball or whatever what the angle is. You blah, blah, blah. Like, you don't really have to think carefully about it. But this is starting to get right at the point where, to me, if I try to just think about what that angle is, it takes too much RAM. My brain isn't quite able to do it. So there's sort of a systematic approach you can take when that happens. And you can make it a lot worse than this. Like, the problem is we have a 45-degree angle. Well, no, the 45-degree angle doesn't come into this. The problem is that we have a 20-degree angle with the vertical, and then a 90-degree angle with this. There's two different, like, those angles are measured off of each other. Okay. And what? And so, what we want to do is just set up a coordinate system and piggyback from one angle to the next. You could do this with 50 things that are referenced to each other and just keep adding those angles up. And if you go counterclockwise, call it positive. Counterclockwise to you, this way. And if you go clockwise, call it negative. And in the end, we'll have an angle theta, and we can just use cosine and sine to represent that unit vector. Okay? It's a nice systematic way to do something like this. So let me draw the coordinate system. Okay, so there's the coordinate system. There's the x-axis and the y-axis. And we need to do this with vectors, and all these vectors' tails have to be at the origin. Since that slot is a line, we could kind of go with either one of these, but I'm gonna choose the one that has the angle shown. Okay, so that's my first reference vector. Okay, and we know that the angle between that vector and this vertical is 20 degrees because that's exactly how it's shown on the picture. Okay. And so theta so far is, well, since we're going to use cosine and sine, we want to go counterclockwise from the x-axis to get to this angle. If you go clockwise, it's negative. And so that would be like clockwise 90 minus 20, right? So negative 70, or you could go all the way around and 290. Same thing. It doesn't, you can do it either way. So theta is minus 70. And then we want something perpendicular to that. So I'm going to draw another vector with its tail at the origin that's perpendicular to the one we just did. Okay. And that angle is perpendicular to that. So we started went minus 70, now we're here. Now we're going counterclockwise 90. So plus 90 gets us where we want. And so theta just turns out to be 20 degrees. If you would have gone 290 to start here, go all the way around, you're at 290 there, positive 290. So another 90, you're at 380. And, you know, that's a big angle, but cosine and sine, it comes out the same. You get the same unit vector. So the unit vector is cosine of 20, sine of 20, or 0.940, 0.342. And so that force vector is r times this. So 0.940 r, 0.342 r. That piggybacking angles thing can be, when you get used to doing problems like that, that can make some really complicated looking geometry just a simple step-by-step process to do. It takes a little practice to get used to it, but that practice is what I'm here for. Any other homework questions? Oh, there was one more part to that. The vector from the wall pin to the slot. So remember I said, no, I didn't say this. I'm thinking of statics. Okay, well, if you want to calculate a vector, so for part B, we're trying to calculate this vector. Okay. So no matter, you can put the origin wherever you want, just calculate the coordinates of those 2 points and then just subtract. Since it doesn't matter where the origin is, we can just put the origin up here, and then finding this vector is just a matter of finding those coordinates. So here's the coordinate system. Let's say that's up at the pin. And we want to find that vector where this angle is 45 degrees and the length is 4. So however you want to do your cosine and use cosine and sine to come up with your unit vectors is fine with me. Because I teach college physics like a lot, I'm pretty used to just always using cosine as the x, always using sine as the y, and just using an angle that goes all the way from the x-axis. You know, that's probably not how you do it. That's not how I did it before I started teaching college physics all the time. But anyways, that angle is 180 plus 45, 225. So cosine and sine of 225 times 4 gives you 4 times cosine of 225, 4 times sine of 225 is 3 points. So negative and negative. 4 times 0.7071 is 2 times 0.141. No, 2 2.828, right? Any questions about that? Okay, let's try to finish mathematical preliminaries today, and then we can get on to dynamics next time. Um, so last time I was talking about separation of variables. We did it for first order and second order differential equations. So separation of variables. One thing that's going to come up sometimes is systems of equations. Like, for example, you could have something like x dot is equal to 5xt, y dot is equal to 2y squared, t squared, and then with boundary conditions. Okay. So when can you solve those? There are ways to solve them. I'm just going to talk about the kinds that you'll see in this class. And there are ways to solve other ones. But key in this class is whether the equations are coupled or uncoupled. In this class, we'll only have to deal with uncoupled equations. So what that means is that, so let me make that a semicolon. What an uncoupled equation means is that each dependent variable stays in its own equation. So an example of a coupled equation would be like x dot is equal to x yt, and y dot is equal to, x squared t squared. We don't have a way to solve these in this class. If they're uncoupled, they stay in their own equations. Then you just solve those as two separate differential equations. They each have their own boundary conditions. Okay, and so it's a system, but to you, it's just two differential equations problems. Separate Okay, so let's go back to the example I showed. Now, well, are those coupled or uncoupled? Those are uncoupled. That's good. And then can we solve? Well, that means we can look at them one by one. So let's look at the first one. Is that something we can solve with separation of variables? Yeah, because you can write this as a function of x times a function of t. What about this one? Can we solve that by separation of variables? Yeah, because it's a function of y times a function of t. And so we'll do this one first, come up with an answer, and do this one and come up with an answer. Any questions about that?
Just
Mhm. Yeah.
notation dot symbol that refers to a rate of change, right?
With respect to time specifically. Yep. So yeah, anytime you see the dot, that means with respect to time. And it's just because in some areas, and dynamics is probably the biggest one, all you thermo too. Yep. That's right. That's right. The main derivatives you take, or the main independent variable, is time, and so it's just a shorthand way of writing what you have to write all the time, you know. But dot always means time. Okay, so now here's where we are in the math preliminaries. That's all I want to say about separation of variables. Okay, so first was ODEs using separation of variables. Separation of variables, and we're done with that one. And now we're going on to derivatives of vectors, as long as the coordinate system is non-rotating. And then we're going on to product rule for vectors. And then chain rule for vectors. Okay, so the next one is derivatives of vectors in non-rotating coordinate systems. And all you do is take the derivative of each individual component of the vector independently. Okay, so let's say that we have a vector u that's equal to, the components are ux, uy, uz. Then to take the derivative of u, that's just the derivative of the x component, derivative of the y component, derivative of the z component. Why does it matter whether the coordinate system is rotating? This is kind of for just to put in the back of your brain for later. Well, this way of writing u, remember, means the same thing as this. So our vector u is equal to ux times I plus uy times j plus uz times k, right? It's I just use a different notation, but that's what it means. And so if you take a time derivative of u, you have to use the product rule here. And it says ux dot times I plus ux times I dot plus uy dot times j plus uy times j dot plus uz dot times k plus uz times k dot. If the coordinate system, so these things, what the hell are those? You know? So if the coordinate system is non-rotating, I dot and j dot and k dot are 0. So it's no problem. Those go away. But if the coordinate system's rotating, we need to come up with a way to represent those. Okay, and that's where all the mess is going to come in. That's where all the complexity comes in when you deal with rotating coordinate systems. Because the thing is, I, j, and k are changing in time, so those time derivatives are non-zero. So for now, just remind yourself to appreciate when a coordinate system is not rotating, because it's going to get really messy. Any questions about that? Okay, so next is product rule with vectors. I guess I sort of used it here above, but remember, this is sort of the key thing with product rule with vectors. There are 3 different ways to multiply vectors. You can multiply a vector by a scalar like we did here, or you can take the dot product of 2 vectors, or you can take the cross product of 2 vectors. And so we need to think of what the product rule means in all these cases. The product rule with vectors. So first, if you multiply a vector by a scalar, so d dt of the quantity, so x is our scalar and u is our vector. Well, this is equal to, another way you can write this, by the way, people would put the xu in parentheses and then draw a line over it to show we're talking about everything inside the parentheses and then a dot over the line. That says a total time derivative of everything inside there. But what would you guess the product rule is here? Without, this is a safe space. Okay, so it would be x dot u plus x u dot. Okay, so it works just like the product rule for scalars. The thing that's going to be an issue in one of these cases, only one of them, is that the product rule with scalars, you're multiplying scalars order doesn't matter, right? So, and it doesn't matter when you're multiplying a vector by a scalar. So, you know, people probably just have different preferences about how they want to think of the product rule. Some people think of it as x dot u plus u dot x. Okay. And with scalars, that's fine. Multiplying a vector by a scalar, that's fine. Multiplying using the dot product, it's fine because order doesn't matter in dot product, but it'll give you the wrong answer if you think of the cross product that way. So from now on, start thinking about the product rule as keeping the order of those two things the same. And then you'll never go wrong. Then the product rule always works exactly like you kind of would imagine it would work, as you would hope it would work. So what I'm saying here is, so this is an aside, but that's not a smiley face. This is serious. This is also equal to x dot u plus u dot x. Okay, but don't think that way. Okay, and then dot product. So say we're taking d dt of u dotted with v. What would you guess the first term is of the product rule? Wrong. So it's u dot dotted with v plus, what's the second term? Yep, u dotted with v dot. And because order doesn't matter with the dot product, that's also equal to u dot dotted with v plus v dot dotted with u. But don't think that way. And then cross product. So d dt of u crossed with v is exactly what you'd hope it would be. U dot crossed with v plus u crossed with v dot. And the whole reason that we don't want to think in that crossed out way is that this is not equal to u dot cross v plus v dot cross u, because this v dot cross u is not equal to, this v dot cross u is not equal to u cross v dot, because order matters with cross product. Any questions about that? And then the last thing is the chain rule. So chain rule with vectors. So the way this is going to come up is, say that you're taking a derivative of a vector that's a function of a function of time. Okay, so f is a vector function. Its argument is, like, say, mostly it's going to come up for us, maybe always it'll come up for us with the g is going to be like a position, x, y, or z, but x, y, and z positions are functions of time. Okay. And this is equal to the derivative of vector f with respect to g times dg dt. So it works just like scalar chain rule, just that one of those derivatives, the df dg, is going to still be a vector. So, and then you're multiplying that vector by this scalar. Here's the way it'll come up. Yeah. Last derivative. Yeah, dg dt, that's right. So it'll come up in dynamics like this. So we know that acceleration is the time derivative of the velocity, right? But what if we know the velocity vector as a function of a position variable instead of the velocity vector as a function of time? Okay. I mean, acceleration is not dv dx, it's dv dt. So if this is all we know, and that would come up in any kind of energy analysis, you get your velocities as a function of position. At first glance, you would think there's nothing you can do. But if you use the chain rule, then the acceleration is equal to the time derivative, and I'll write it in that form of that I have of defining the chain rule. That's the derivative of the velocity, which is a vector, and it's a function of x. And so we can write that as dv dx times dx dt dx dt is just the x component of the velocity. And so the acceleration is dv dx times the x component of the velocity. And doing it that way, we can take the time derivative of the velocity to get the acceleration without ever knowing what velocity is as a function of time explicitly. That's going to be really useful because, acceleration is the key to is the key to putting kinematics together with forces and masses, because that's how you go through Newton's laws, is through acceleration. Any questions? Okay, have a good weekend.